Revisiting the ICTS again. And indeed, my talk today is on Euclidean wormholes, baby universes, and unitarity in quantum gravity. Please feel free to interrupt me at any time. If I'm running out of time, I'll just try to say that let's hold the questions to the end. Okay, so, since about now, oops, what's happening to my cursor? Yeah. Now, ever since the 1970s, one of the major problems in theoretical physics has been to understand the black hole information puzzle, which is really the question of whether quantum mechanics is unitary in the presence of gravity. So just to remind you very quickly, already in the early 70s, Bardeen, Carter, Hawking, and Bekenstein enumerated the laws of black hole mechanics. Those are these things here, which are classical rules that say, for example, that if you insert a certain amount of mass into a black hole, the area changes. So that delta M is kappa delta A. Kappa is the surface gravity. The change in the area is always non-decreasing. The area is always non-decreasing. And kappa, the surface gravity, is constant at the horizon. And these rules are in formal analogy to the laws of thermodynamics. And then, of course, a couple of years later, Hawking showed the existence of Hawking radiation. You have a black hole horizon, and you pair produce just outside the horizon. One member of the pair falls in, one falls out, and you can show that, at least in effective field theory, the radiation looks thermal. So from this, you conclude that, at least in effective field theory, black holes act like black bodies. The odd thing is that black holes are, of course, solutions, like Schwarzschild black holes are solutions to the vacuum equation of motion, which raises the question of, how this is coming about. Especially so because, another lesson of 20th century physics is that anytime you see a thermodynamic system, you really should be seeking the underlying statistical physical description. In other words, there should be a large space of complex microstates, e to the s, in fact, e to the entropy microstates. And the thermodynamics should arise as sort of a universal, coarse-grained, effective description. So an open question that we would really love to understand in detail in any quantum theory of gravity is the following: is unitarity of quantum mechanics preserved by quantum gravity? And a way of saying what that means is, can you decode what fell into the black hole from the Hawking radiation? So you watch the radiation come out, and you would like to infer whether the thing that went in originally was elephants, dictionaries, whatever they may be. So you'd like to sort of know that decoder. Now, actually, in some sense, it's clear that actually you should be able to do this. So let me explain a very general argument that shows that you should be able to decode the Hawking radiation, and then tell you what's the challenge with that argument. So let's first of all suppose that there is a statistical mechanical description of black hole microstates, so that the entropy arises from some underlying space of discrete microstates. So in quantum mechanics, the spectrum of the Hamiltonian is generically non-degenerate up to symmetries. So you should conclude from this that each of these microstates should have a unique mass up to symmetries, rotations and stuff. But in gravity, mass is measured at infinity, essentially through a Gauss law. And so this immediately tells you that a very, very precise mass measurement should allow an asymptotic observer to actually measure the black hole microstate. You know the mass, so therefore you know the state. So now let's ask how precise that mass measurement would have to be. So suppose the entropy is SFE, then that's really saying that the number of states in whatever your energy resolution is, call it delta E, should go like E to the entropy. And so if you take, let's say, the energy resolution of your measurement to be some multiple of the Planck mass, or whatever, string mass, whatever you want, then you'll find that the level spacing will go like E to the minus entropy to fit this number of states. In other words, there's basically a super Planckian energy, the gap is really tiny. The gap is of order e to the minus entropy. So to measure, what do you need to do to measure masses, energies with such precision? Again, using quantum mechanics, you know that delta T, delta E is bigger than or equal to h bar, which tells you the amount of time you require to measure energies with the precision of this gap goes like 1 over the gap, which goes like e to the plus entropy. Now, finally, the entropy goes like the area of the horizon divided by 4 g Newton h bar. So if you send h bar to 0 to take the semiclassical limit, this time scale is going to infinity. Okay, so what does all this say? At some semi-qualitative, quantitative, or qualitative level, all the information about the state is clearly present in infinity. You can measure it using a simple observable, the mass. However, the semiclassical observer is not going to be able to access it because the time scale is going to infinity as h bar goes to 0. And this will act as if the interior of the black hole is causally disconnected. So the bottom line from this, and you can construct other arguments of this kind. So the bottom line from this kind of argument is that you should expect that all the information about the states of the black hole is in fact available at infinity, but semi-classical effective field theory probes will give you universal measurements. This is one such example of such a semi-classical probe. It's just measuring the mass. You can extend this, finite endpoint correlation functions and things of this kind. So this is why you lose the information from the black hole, even if it's actually there. Okay, so and of course, to summarize further, so that's in addition to what I just described, I've not described here the dynamical phenomena of things like scrambling, chaos, and thermalization, which makes things even more complicated, because this means that the dynamics of the formation of the black hole, of the microstates, mixes information about incoming states, making it very difficult to access using simple observables. So there's, as you know, there's been a lot of work in the last decade, enumerating and understanding these kinds of dynamical phenomena that mix up the information of the states. So from this narrative, it would appear that black holes are just like any old complex system that loses, quote unquote, information through coarse graining. The surprise about them is they just have a ridiculously dense density of states that's non-perturbative in the Newton coupling, and this is the source of all the confusions we have because it's just so dense. And so the core problem is sort of finding these states in quantum gravity. Okay, so from this perspective, to see the unitarity, in the end, you do need to know the microstates. Because, how else do you see that it's unitary? If it's elephants or dictionaries that made the black hole, if you need to know which it is, then you need to know what the microstate is. Otherwise, how could you possibly know? So from this perspective, the semi-classical effective field theory description is simply not going to be enough to fully reveal the unitarity. I mean, you may be able to argue for unitarity, but to reveal the unitarity in the sense of being able to decode the microstates, you are going to need the microstates. The semi-classical effective field theory description is not enough. So against this context, there's been an interesting new development in the last few years, which involves an information theoretic perspective on the same problem. So if you take the calculation of Hawking and Hawking's original calculation of effective field theory and compute the entanglement entropy of the radiation here coming out of the black hole. So here again is the pair production process. One quantum goes in, one quantum goes out. So when you have Hawking radiation produced this way, the outgoing quantum is entangled with the stuff that went in. So, well, it looks like there's some entanglement entropy in the radiation. If you take for granted the original effective field theory calculation of Hawking, the entanglement entropy associated with this outgoing quanta, the radiation, will keep increasing monotonically with time because, it's entangled with something, the stuff goes in, that stuff is, you're not looking at it, so it's the usual story. However, on very general grounds in information theory, it ought to be the case that this entanglement entropy cannot increase monotonically over time. And that's because of the property of monogamy of entanglement. So this implies that after about half the radiation has emerged, its entanglement entropy must decrease again, simply because the number of interior bits inside the black hole that you can be entangled with is decreasing. So there's just not enough stuff to be entangled with to sustain a continuously increasing entropy, and therefore, eventually, the entanglement entropy of the radiation must go to 0, okay? And this is very similar to the reasoning that Samir Mathur and Alheri, Polchinski and Sully used to argue for macroscopic corrections to the black hole physics after half the radiation has emerged. So from this perspective, you might think that a test of unitarity, or at least of some aspect of unitarity of quantum mechanics, is to recover somehow this page curve, which means that the entanglement entropy goes up and goes down. So an interesting new development over the last couple of years is that it may be possible to see unitarity, at least in as much as you're talking about the page curve. I'm not actually recovering the microstate. I'm sorry, in the page curve, it may be possible to see unitarity directly in semi-classical gravity. Honestly, that's a real surprise to me because I would have expected that even to see this sort of decline and see the monogamy of entanglement, you may need to know something about the microstates, but perhaps not. Maybe semi-classical gravity can actually reveal that, and that's been the interesting development of the last couple of years. But at the same time, we've also learned that some gravitating theories appear actually to be dual to ensembles of theories, not to a single unitary theory. So these 2 points are somewhat in tension with each other, as I will discuss later in the talk. And what's interesting is that both of these developments, this unitary page curve and this sort of ensemble description of gravitating theories, arise, both of them, from a recognition of a novel role for space-time wormholes in quantum gravity. So the same phenomenon, these space-time wormholes, seems to be producing these 2 results that are kind of slightly pushing against each other, as I will discuss in a bit. So, so I'm going to discuss that set of ideas today. So most of the work that I've done on the subject has been in collaboration with several people. Arjun Kar, who was a grad student and is now moving to UBC. Onkar Parikar, who was a postdoc and is now at Stanford. Gabor Sharoshi was a postdoc and now is at CERN. Tomonori Ugajin, who used to be a postdoc and now is an assistant professor in Kyoto. And Simon Ross, who is a Durham, as you guys know. So great. So I'm going to discuss this this pool of ideas from various perspectives. So I want to start off by thinking about the so-called island formula and the page curve. So remember, I told you that if I take the naive calculation by Hawking, the entanglement entropy keeps increasing without bound. For evaporating black holes, entanglement entropy had better increase of the radiation, entanglement entropy of the radiation better increase than decrease because of monogamy, namely because there aren't enough bits left inside of the black hole to be entangled with after a while. And for black holes in something like anti-de Sitter space, the entanglement entropy should increase and then sort of flatten out because ADS black holes, as you know, come to equilibrium with their radiation. So once they've come to equilibrium, you're expecting the entanglement entropy of the radiation to, to be a constant. As a function of time because it's in equilibrium with this thing with a certain number of bits in it. So there's been a proposal for recovering these kinds of unitary looking page curves using something called the island formula, which works as follows. So suppose A is the region, is a reservoir containing the radiation that's come out. And this reservoir is interacting with some gravitating region. Now what you do, supposedly, in semiclassical theory, to compute the entanglement entropy of A, is you consider A and an island, a disconnected island, or set of islands sitting inside the gravitating region. You take the union of the radiation region A and these islands B, and you compute the effective field theory entropy on the union of A and B. And then you add to it the area of the boundary of B divided by 4G Newton, and then you minimize, you extremize, and then you minimize over possible choices of B. So this formula will, as it turns out, reproduce for you this page curve and of the correct form. When you look at it carefully, you might wonder, if someone gave you this formula at the end of the day and you sort of applied it, you'd think it was sort of answer analysis because by construction, it's going to give you the correct page curve. But the real evidence for this somehow comes from the replica trick and doing Euclidean and the Euclidean calculation of entanglement entropy using the replica trick. We'll talk more about that later. And basically, most of the evidence for this has come in the context of JT gravity in 2 dimensions, so a relatively low dimensional gravity, but very interesting that it can be derived. So today, and here is a list of the cast of thousands who has derived these interesting results. So today, the first thing I'd like to do is to try to see whether we can generalize these results in 2-dimensional gravity a little bit to 3-dimensional gravity and the BTZ black hole. So why do we want to do that? Well, 3-dimensional gravity is sort of more interesting than 2-dimensional gravity. There's more in it. There are black holes, there are other kinds of interesting things in 3-dimensional gravity. There are multi-boundary wormholes in 3-dimensional anti-de Sitter space. It is an interesting zoo of objects to play with, so we can test these ideas there. Secondly, in 3-dimensional gravity, there's no local graviton, so we don't have dynamics. So once again, that's very helpful. And you can construct all the solutions using global identification. So I'm going to use that fact to try to reason out everything I'm going to say today in pictures, even though you can calculate everything. It's very helpful to be just imagining it using pictures. So that's what we'll use for today. Okay, so so let me remind you what the Penrose diagram of these black holes looks like. So here is an anti-de Sitter, 3-dimensional anti-de Sitter black hole. So we're going to imagine here that there is a, these are the horizons, the dashed lines, and here is the past future singularity. And here I've drawn a picture of a brain trajectory. So if I inject a brain from the past, it sort of goes like this and comes out over here. So this is the setup. And we're going to imagine that we have the system and we stick a little radiation reservoir, we're going to cut off this boundary just a little bit and put a little box here that collects the radiation over there. Okay. And then our plan is to derive or justify the island formula in 3 dimensions using conventional holographic ideas. And then, so we're going to try to use standard holography, standard Ryu-Takanagi formula, and things like that to derive or explain where this island formula is coming from in this case. So let's look at this a little more closely. So here's going to be our model. So here is a time reflection slice of the BTZ black hole. As you know, this thing is an eternal black hole. So it's a wormhole between 2 asymptotic regions. So here's the region A, here's the region B, and we're going to collect the radiation over here. We're imagining that we cut the thing off and there's a little bit of escape into a little reservoir on this boundary here with weak gravity in it. So that's going to be a radiation reservoir. The other thing we're going to do is we want to make a model of a single boundary wormhole, black hole. So to do that, we're going to imagine that we cut off the second asymptotic region behind the horizon and replace it with some end of the world brane, which has, various kinds of possible states on it. This is sort of following the kind of logic of Kurkulu and Maldacena. So why is that a reasonable thing to do? Well, we can go back and forth on that. But actually, if you look at many of the honest-to-God black holes of string theory, things for which the states have been counted, like the ADS3 black holes made from the D1, D5 string, or the 4-dimensional and 5-dimensional black holes made by intersecting D-branes, then in these cases, in the end, behind the horizon, somehow there is some bound state of D-branes of some kind. So you could imagine this as a model of that system of branes. And so in this setup, we're going to imagine that the microstates have been entangled with K Hawking quanta. So the quanta have been radiated, so they're out there. And we're going to distill that entanglement into subspace and write the state of the system, some possible states of the radiation entangled with the possible states of this end of the world. So that's going to be our setup for the state of the system that we're going to look at. And we will mock up radiation. Since there's no real dynamics here, we're going to mock up radiation by imagining that we increase or decrease K. That's like increasing or decreasing the size of the reservoir. We increase or decrease K, the number of Hawking quanta, and that's going to be a proxy for the radiation process. Okay. So the next step for us is the following. So as I said, we have this end of the world brane whose states are entangled with the radiation to infinity. And so the next step I'm going to do is to treat that end of the world brane as itself described by a CFT. Again, the reason why this is natural to do is if you think of, for example, the D-branes that make the microstates of the ADS3 black holes, like the D1, D5 string, their effective theory on the world volume is indeed a CFT. So we're going to think about the D-brane, the brane here, the end of the world brane itself, as being described by CFT. And then we're going to replace that CFT by its holographic dual. So here, here was the end of the world brane that was truncating this geometry. So we replace that by this disk. So, we put this disk inside that. And this disk is going to be the holographic dual to this brane. And by the way, it can have a central charge, a length scale, and a Newton constant that are different from the original states, because this is really the dual of the end of the world brane, not the dual of the original theory. And so it is what it is. And so you've got to splice these geometries together. And we can further say that if you trace out the Hawking quanta, right? So if you take out the Hawking quanta and just look at the theory of this brane, because the state of the brane was entangled with the state of the Hawking quanta, on this inception disk, as we call it, there is going to be a black hole. That's because this is an entangled state. So basically, this thing looks as though it has a black hole because the state of the brane looks maximally mixed when you trace out the radiation. Okay, and the entropy of the density matrix will then go like log K, and you can increase K to increase the to effectively increase the radiation. Are there any questions?
What was K again?
K was the number of Hawking quanta. So it's a proxy for the amount of radiation. Okay.
Sir? Can you explain the last statements again, that the configuration of integrating out the Hawking radiation can be analyzed as a setup of a black hole?
Yeah. So observe that we said, whoops, that the state of the brain are entangled with the state of the radiation. So if I trace out the radiation, it will leave the state on the brain in a density matrix. And that maximally mixed density matrix, if we describe it holographically, will be described as a black hole. So, okay, great. So then the next step is the following. So now I want to purify this black hole. And the way you purify a black hole in ADS-CFD is you imagine that there's a thermal field double. And so here, this was the end of the world brain. We had replaced the interior of the region with some other, with a black hole in this auxiliary or induced or holographic ADS space. And now if we purify that, hold on, let me just finish this. And if we purify it, then we have to introduce some auxiliary system with which that brain is entangled. So here is that auxiliary system over here with which it's entangled. And in some sense, this auxiliary system is actually naturally identified with the original radiation. Remember, the brain was actually entangled with the radiation. We traced out the radiation, made it into this density matrix, and then we're purifying again with some auxiliary system. So this auxiliary system is kind of naturally identified with the radiation. So in some sense, you could say that this real and this inception space are kind of living on top of each other. And it's kind of a realization of the ER equals EPR idea, if you like. So one way of thinking about this is when you remove the radiation from the original space instead of kind of put it into a reservoir, you kind of split the bulk dual and remove all the quote ER equals EPR bridges. And that's what's being described by this inception geometry. So this is now like a long wormhole. And here is the geometry drawn with one asymptotic region. This is the sort of radiation asymptotic region, or the purifier asymptotic region. Here is the end of the world brain. And if you were to take an equal time section through it, the geometry would look like this. It's a long wormhole. So you have the original boundary, you have the black hole horizon, you have where the end of the world brain was, then you have the inception geometry, that has a horizon, and then you have this radiation boundary. There was a question.
Yeah, so I was wondering, how do you fix the temperature of the brain CFD?
Right. So that's fixed essentially by the number of Hawking quanta. So there's a certain amount of entanglement, and what you do is you change the amount of Hawking quanta, the net amount of Hawking quanta you're entangled with, it changes the temperature of the brain CFD.
Can I ask a question about the previous slide? This
but this slide, one more up.
No, the slide with the gray shaded region. The next one.
This one.
The next one.
This one.
Yes, yes. This gray region, is it correct to think that it lives inside the black hole? The red, excuse me, the circle on this picture is a spatial circle. So whatever is living to the left of the most narrow circle is sort of inside the black hole. Is that correct?
Yeah, it's kind of a geometrization of the black hole microstate. So let me tell a parable, so to speak. So when D-branes originally came out and people started talking about black holes made from D-branes, and one tried to imagine what falling into. So imagine that you have a bunch of D-branes making a black hole. There's a horizon. You make the string coupling smaller and smaller and smaller, so that the horizon becomes about the Planck size, and then there isn't really a classical horizon. But the black hole is still there in some sense, because you have these D-branes sitting there and they made the original black hole. So in some sense, the physics has not gone away. So where would the inside of the black hole be? In some sense, it has to be sort of in the inside the D-branes. So how to put this, there's when you take D-branes and you move them apart from each other, you're in the Coulomb branch of their theory. And when they're on top of each other, if you sort of move within the D-branes, you're kind of in the Higgs branch of the theory. And you might imagine that what you're talking about is that the inside of the black hole is kind of made as an effective description of that internal dynamics of the D-branes. So this is a geometrization in this setting of that internal dynamics of the brains that make up the black hole. Did that provide a suitable intuition? Okay, well, anyway, that's how I think about it. It's the one challenge with these Zoom talks is you can't see people's faces. So please do, speak up and say what you're thinking, because I can't tell from people's faces, what they're thinking. Great. Okay. So the next step, where was I? Okay, I was here. So we had talked about sort of purifying this internal black hole. Okay, next step is to do the following. I want to now compute I want to describe the same system in its Euclidean version. So in the Euclidean version, if I talked about the Euclidean black hole, the Euclidean black hole geometry is a cigar. So you see this outer peach-colored thing. Cigar or bullet, whatever that is. And normally, if I had the full black hole, this rim would be a full circle, and you'd get the full cigar geometry. What we've basically done in Euclidean terms is we've chopped off the geometry somewhere. Notice that this circle here is Euclidean time. So we've chopped off this thing somewhere. And this is where the end of the world brane sits. And this inception geometry, this sort of dual to the brane, the end of the world brane, is another black hole geometry. So it's another kind of Euclidean, cigar that's kind of stuck to it in this way. So the angular direction here is supposed to be Euclidean time. So what we need is a solution to the equations of motion of this form. So the way we find these solutions is by using the Israel junction conditions. We impose that there's a BTZ metric on both sides. But as I said earlier, you're allowed to have different horizons, different ADS scales, and different Newton constants, because this peach-colored thing is the dual to the original CFT, if you like, making the ADS space, and this gray-colored thing is the dual to the end of the world brane. So there's a certain amount of calculation to be done to find that you can find a solution where the induced metric is continuous. And if you want, you can take the induced stress tensor to be entirely holographic on the other side. So I won't work through the details of finding that solution. You can find that in the paper. So if I was to draw this, if I was to draw the same thing, from looking from the outside here, then what here I am drawing the Euclidean disk. This is Euclidean time going around, and this is the trajectory of the end of the world brane in this kind of picture, looking from the outside. Okay, so this is trying to help you visualize, where the end of the world brane sits and so on. So the next step is to think about, in this setting, how you compute entanglement entropy. So we're going to propose that in this kind of setting, where you take the holographic dual of these end of the world branes, and so you get these long wormholes, that the standard rules for computing holographic entanglement entropy persist. So in other words, suppose I had this region A1 and I wished to compute its holographic entanglement entropy. Ryu and Takanagi told me that I should find some sort of minimal surface, extremal surface in the bulk, that's this orange line, and compute A over 4 G Newton. But if that minimal surface happens to hit the end of the world brane, then what do? Well, you might imagine that I should then include the entanglement entropy of the segment of brane that's contained within this thing. And then, and here in our setup, that segment of the brane is gone. And instead, the entanglement entropy of this segment of the end of the world brane is itself described holographically by another RT surface within this inception geometry. So strictly speaking, what happens is that it's as if you send in this minimal surface, and then it's refracted at this boundary, and then you have to take the refracted surface and add it all up, and you add up the total amount, and the total amount A over 4 G Newton plus A prime over 4 G Newton prime, because remember, this induced geometry, this inception geometry can have a different G Newton. You have to add that up, and that's supposed to be the entanglement entropy. Okay, so that's the proposal. And in this language, the page transition that causes the entanglement entropy to increase and decrease follows the following way. So we have this sort of extended wormhole, and this is the original black hole horizon. And this is the horizon associated with this radiation. It has an A over 4 G Newton, which is log K, and this is the original black hole entropy. So if I take this radiation over here, right, the radiation being the thing that purifies the end of the world brane, the thing that purifies black hole microstates, and ask, what is its entanglement entropy? Well, Ryu and Takanagi would tell me I should find a extremal surface that's homologous to this surface R and compute its area over 4 G Newton. And if I find that there are multiple surfaces, extremal surfaces that are homologous to R, I should take the one that has the minimum size. So here, there are two surfaces that are homologous to R. There's this dashed blue, and there's this dashed black, the original black hole horizon, the inception horizon. So you can imagine what's going to happen. If I construct an evaporation protocol where I take K, initially it's small, there's not much radiation, and I increase K and make it bigger and bigger, it's going to happen that when K is small, the entanglement entropy of R is dominated by this horizon, and then when holographically, and when the and when K gets very large, it's actually dominated by this horizon. So that would tell you that the entanglement entropy here would increase with K as you increase K, but once it hits the actual black hole entropy, it'll stabilize. That's what you want to see in terms of reproducing in this kind of toy setting, the Page curve. Someone had a question, I think.
I just couldn't follow up all the statements due to the lack of connectivity. So you replace the brain by its holographic dual,
yes,
which is A prime.
Yeah.
Okay. And now
sorry, the holographic dual is an entire shaded region.
Okay.
And in that shaded region, there is a horizon. So if I take this radiation boundary and I compute its entanglement entropy, according to Ryu and Takanagi, I should find a minimal surface, an extremal surface that's homologous to R. There are two extremal surfaces here homologous to R. There's this dashed blue line, which is the horizon in the inception geometry, and the dashed black line, which is the horizon in the original BTZ geometry. And the two compete for, to dominate the entanglement entropy. Did that help?
So why is B prime geometry dynamical?
It isn't dynamical in our setting. You could try to make it dynamical by doing the entire dynamical process. So we're doing the sleight of hand that a number of people have been doing, right? Where you take K and you make K small and big. You imagine the black hole in equilibrium with a certain amount of radiation, which you control by controlling the size of the radiation reservoir. And then increasing and decreasing the amount of radiation you have in your hand is the proxy for the actual dynamics. Does that answer the question?
Thank you.
Okay.
Thanks.
So Vijay?
Yes?
So if I'm imagining still what's going on just using the dual CFT,
Yeah.
I'm a little confused about item 3 here.
Mm-hmm.
So, because item 3 sounds like the gray shaded region, you're saying that it's possible that the dual CFT on the left has a varying central charge.
Yeah.
So what sets that central charge?
So
and the temperature of the CFT that's on the left?
So this is the trickiest point in the way that I've presented things here. So that central charge is set, as you know, if I take the brain, there's the number of states of the brain, there's the there's its coupling, this, that, the other. We're varying various things in order to be able to get the solution. You can avoid this awkwardness, and this is definitely an awkwardness, by agreeing that the end of the world brain is a tension and has a non-holographic part of its stress tensor, right? So you can make modifications to the setting where you don't need the sleight of hand. So what happens is that this is, after all, a toy model, and there are many alternative toy models that basically give the same result. So here I'm picking the simplest setting, but in this simple setting, what you need to do is you change K. You need to change, if you like, in some sense, you're focusing on a certain number of degrees of freedom of this end of the world brain, and you have to sort of modify, its couplings, this, that, and the other, as you change K in order to get the smooth geometry that connects between. You can, again, as I said, you can change that by adding a, basically a stress tensor on the brain. So, but I didn't do that in the particular setting that I'm describing here. Maybe I should have done that. It would have been easier to describe.
So what does a non-holographic part of the stress tensor do to this picture?
Nothing essential. Changes the brain trajectory. So because there's a tension on the brain, the actual trajectory it follows in the geometry will be slightly different. And that makes it possible to splice the things together without having the sort of varying of the cosmological constant on the two sides. again, we have to understand that this is a toy model. So all of these models that we've been talking about lately in the community have been toy models of various kinds. And really, in the end, I do think what we really want to do is to answer these questions with an honest-to-God, fully string theoretic setting. It would be really nice to make progress thinking about this kind of thing with, let's say, I don't know, the D1, D5 system that actually makes ADS5. So I think here, this illustrates that the fact that the same results obtain for different kinds of choices of the properties at the end of the world brane suggests that fairly universally, that kind of thing will work out. That's not a complete answer to your question, Emil, but I hope it helps.
Okay, thanks.
So the next step is to think about the islands that you get from this in the language of this sort of island formula. So if you start out and you look at the radiation, initially for small k, when there's not much radiation, this horizon here is the one that dominates the Ryu-Takenagi formula. In that case, what happens is that the entanglement wedge of the radiation is this region. It doesn't contain the interior of the black hole. But late in the radiation, the actual black hole horizon becomes dominant. And so as a result, the entanglement wedge of the radiation includes this green region here, which is the black hole interior. So what that says is if you follow the standard entanglement wedge reconstruction methods of ADS-CFT, this would say that early on, you can't recover the inside of the black hole. And late, once, basically after half the radiation has come out, so to speak, you can recover from the radiation the interior of the black hole. So that's what this would say. So far, the way I talked about all of this is by just proposing that you could use the, extend the RT formula. And I was just following my nose and saying, here's some three-dimensional gravity stuck to another three-dimensional gravity with a junction condition. You can solve classically the geometries. So the RT formula should apply in the standard way with a refraction condition across the boundary where you had this end of the world ring. But it would be nicer to actually show this in some systematic manner. And you can do that, you can prove that prescription by using the replica trick. So the way you do this is here is this, again, this Euclidean geometry. This is the, this is the radiation, if you like, boundary. This is the original boundary. So to compute, let's say, the third Renyi entropy, what are you supposed to do? Well, to compute the density matrix, what you do is you cut open this thing in Euclidean time over here and then do the path integral. To get the, let's say, the third Renyi entropy, you glue this cyclically along this cut, and then you'd fill in this cyclically glued geometry with some saddle point in the bulk. And the replica symmetric saddle point ought to dominate the calculation. So I'm leaving out the details, but it turns out that there are two replica symmetric ways of filling in these boundaries. So once again, here's the boundary with 3 places where I've done this cut and joining. And here's again the boundary with 3 places where I've done the cut and joining. And there are 2 bulk solutions. There are 2 replica symmetric saddles. And this one turns out to be the one that is with the fixed point on the inception side is the Hawking phase, and this is the Page phase. And then what basically happens is that if you do the gravitational path integral, and you can think about this as a kind of wormhole if you like, but if you do the Euclidean wormhole if you like, so if you do the gravitational path integral, these 2 things exchange dominance, and this when k is small, this when k is big, and then following Lefkowitz and Maldacena as n goes to 1, we recover the von Neumann entropy from the area of the fixed point of the replica symmetry. So by the replica trick, the prescription that we're trying to suggest seems to hold. So now we can have some fun with this prescription and talk about some fun things. So I'm going to do that and then sort of try to delve deeper into what all of this might actually mean. So here's one thing you could do. You could ask how, in what way is the secret of the interior of the black hole stored in the Hawking radiation? So for example, if I take part of the radiation in this model, can I recover part of the interior? So here's one way of thinking about it. I might imagine that I consider, let's say, the part of the radiation somehow came out early and part of it that came out late, or in this sort of geometrized picture, I split the radiation into two parts, let's call it R1 and R2, and then, you know, I sort of keep them separate like this. Okay. So now in this kind of language, you'd split the radiation Hilbert space into multiple components. And then in this inception side, remember there was the black hole, and the black hole was purified by having some radiation. Now I can split the radiation into two parts and have this kind of setup, right? This is a different model of the radiation, if you like, where I have R1 and R2 being two kind of separated pieces of the radiation. So, and these kinds of solutions can be constructed basically because, again, 3D gravity, everything involves identification to the hyperbolic disk, so you can construct these kinds of things. So you could ask, can you reconstruct part of the black hole interior with part of the radiation, so that's this R1? So let's do that. Suppose you look at R1, then early in the radiation, the entanglement wedge lies behind this dashed horizon over here, just this part of it. But late in the evaporation protocol, another minimal surface develops. Now there's this purple line, and this purple line is also homologous to R1, so it's a valid RT surface. And it turns out that late in the radiation, you have this region, this purple shaded region, that can be reconstructed into as the entanglement wedge of the radiation R1. So there's a partial island in the language of the island people, which is that there's a partial region inside the black hole that appears to be recoverable from this part of the radiation. Now, then you can keep going, and if I take just the radiation R2, region R2, you get this is the entanglement wedge over here, and so there's a region here in the middle. This, if you look from this side, from the right side, that's this purple region here. So this purple region is neither in the entanglement wedge of R1 nor in the entanglement wedge of R2. But it is, of course, in the entanglement wedge of the union of R1 and R2, because the original black hole horizon is homologous to the union of R1 and R2. So what this tells you is that if I have complete quantum access in this language to R1 and separately to R2, you cannot reconstruct the interior. Whereas if you have joint access at the same time to both of them, then you can reconstruct the interior, which points to a kind of quantum sequence sharing scheme in the radiation. So one oddness about this, about this entire island setting, that I have to say I do not fully understand, is it's sort of very strange that one might imagine that if you pick a piece of the radiation, you can reconstruct some actual localized piece of the interior geometry. Who ordered that? Why was it this piece, not that piece, and things like that. So, so there's something interesting going on here, where in these pictures, there's a geometrization of the entanglement, where you're distilling a part of the interior into this part of the radiation, distilling some other part of the interior to this part of the radiation. And I don't think we fully understand yet as a community, what that means, how that happens, and so on. So anyway, let me summarize this. Whoops, I'm going backward.
So can I ask a short question?
Sure.
I didn't understood why the second portion was, I thought it was the holographic, it was the purification of the first part. I didn't got how it encoded the Hawking radiation. Maybe I missed a few points.
So
if it's getting late, I can.
Yeah. So the idea was, so I think you're asking in what sense this stuff is supposed to be the Hawking radiation, if it's actually just a purification at the end of the world brain. Is that your question?
Yeah. Yeah.
Okay. So let me try to answer that. So, so originally we have the radiation. We trace it out and get rid of it. Then the end of the world brain is in some density matrix. Then I take the density matrix and I purify it by entanglement with some other system. Okay. But that other system, but that other system, if it purifies the black hole, has to be unitarily identical to the Hawking radiation, because really the black hole is purified by the Hawking radiation. So really this other auxiliary system is, if you like, is a representation of the Hawking radiation. That's why we're calling it that. So in a lot of this literature, that's what people are doing, right? They take some auxiliary system, which happens to be entangled, which purifies, let's say, this end of the world brain. And then they'll say, well, that's like the Hawking radiation. Well, it's like the Hawking radiation in the sense that it's the purifier. The original purifier was the Hawking radiation. And this is just a map between Hilbert spaces. You cook up a convenient description of the Hilbert space, which purifies the end of the world brane. And it's some, you can think about it as some unitary rotation of the original Hilbert space of the Hawking radiation. Does that answer your question?
Yeah, thanks a lot, sir. Just a small question again. Why is it that only, so how much of the island can we recover from the region R1? Meaning, what's the extent of the partial island?
So if you're asking for the area of it and how it's related to the size of R1 relative to R2, I don't know the answer to that question. That can certainly be worked out, but we didn't, so I can't give you an easy answer.
Okay, sir. Thank you, sir.
Okay, so let me summarize very quickly.
Can I ask a quick question about the previous slide? So this is a different purification of the same state of the Hawking radiation, yes, or it's a different state of the Hawking radiation corresponding to a different initial brane? What is this picture supposed to tell me?
Yeah. It's supposed to tell you that, so I'm going to rewrite the Hawking radiation in a different, after some unitary rotation that's being split into two parts, R1 and R2. Okay, so what I'm going to do is, if you give me the radiation, I mean, one of our problems with decoding, if you like, the Hawking radiation is we don't know, I mean, the information is all mixed up in it. So now I'm going to mix it up. So I'm going to do some rotation on it, if you like, and produce a different basis for it in such a manner that I split it into R1 and R2. So it's a different representation of it. And I imagine it, at least in my head, without proof here, that this is some funny unitary rotation of the Hawking radiation that clarifies its structure. That's the comment I was making. That's kind of weird that if I take R1, in all of these island pictures, it's kind of weird that you take a piece of the radiation and you say, oh, it reconstructs this little geometrically localized piece of the interior. What does it even mean? How does that happen? And I think this is the kind of thing that's happening, that you're picking particular bases that do that, and that the holography is finding some interesting trick to enable us to do that.
Okay.
Okay, so the next thing, so let me just quickly...
Sorry,
may I continue to, I realize I'm kind of running out of time.
Okay,
so
please.
I think I have 15 minutes because we started 5 minutes late. So I'd like to use that time to say a little bit more, and then could we take your question afterwards? So just let me quickly summarize. So basically, we try to use here standard holography in 3 dimensions with some novel features, such as this Inception for the end of the world brane, to extend the entanglement phenomenon to 3D gravity. And that we try to justify this using the replica trick. And then as a fun application, try to argue that the radiation implements a kind of quantum secret sharing scheme, so that you need simultaneous access to all of it to recover the black hole interior. Now, a lot of the island literature, including this, is a little confusing from many points of view. You have to introduce various novelties, like you have a radiation reservoir without gravity, where you collect the radiation, then you entangle the stuff, and then you've got to figure out how to stick a region without gravity to a region with gravity. In our case, the novelty was we had to stick 2 regions with different kinds of gravities and different Newton constants to each other, all of which makes you feel like, do I really believe all of this in a fully considered quantum gravity? So it's useful to have an even more pared down setting where everything can be made completely explicit and clear. So I'd like to describe one such setting. This is from a pair of recent papers with Arjun and Tomonori. So just to really clarify this to its absolutely simplest setting, it's useful to consider a scenario where you have 2 disjoint universes. So there's no fuss and mess with how you stick things together and sew them and stuff like this. You have 2 universes, A and B, and we will suppose that B carries gravity, but otherwise both of them have a CFT living on them. So A is just a CFT, and B is a CFT plus gravity. I'm not saying any words about radiation or anything. It's just 2 universes, one with gravity and one without. There's a total effective field theory Hilbert space, HA times HB, and I can compute partition sums and stuff like this. And on A, that's just simply the log of the partition sum, is just the log of the quantum field theory. On B, I'm going to take gravity to be semiclassical, because here our interest is in semiclassical gravity. So the log of ZB is going to be the gravitational action on B, plus the log of the CFT partition sum on the background given by this metric on B. So that's the effect, semiclassical gravity plus effective field theory setting on this. So now what do I want to do? I want to entangle the gravitating and non-gravitating universe. And because it's all on 2 dimensions and everything, I should be able to do all of these calculations explicitly. No fuss and mess about splicing conditions, gluing conditions, conformal welding, anything like that. So I'm going to construct an entangled state. So I are states of A, psi I are states of B. I'll take pi to be some thermally weighted thing for specificity. I'm going to take universe B to be a CFT plus JT gravity, because this is the most trivial setting you can do calculations in. So there you go. There's an explicit action for the gravity, and then there's a CFT. And then if I want to compute in this entangled state the entanglement entropy of the entire universe A, then I should compute trace rho A log rho A, where rho A is the density matrix of A. Right? And so this equivalently is the limit as n goes to 1 of the Renyi entropies in the usual way. So we can write this out by hand. So what is trace rho A to the n? It's a product of these probabilities pi, of these coefficients pi, times a bunch of overlaps, because if you trace out I, you're going to find out when you do the sum on I, you're going to find out that you get a bunch of overlaps, psi I, 1 psi I, to basically states on B. So the next step is then, remember these states psi I are states of the universe B. So to construct those overlaps here, then what can you do? You can take universe B and you can prepare states on the equator of that universe by inserting operators at the north and south pole, and then do the path integral. So that computes a 2-point function in the sphere. And so there's a bunch of 2-point functions in the sphere in B, and then we've got to sum these things up multiplied by some weights. So normally, if you do this path integral calculation, well, let's say for the second Renyi entropy, what you would do is you would put a cut in universe A, and then you would take rho A squared. This is what you would do. And the universe B would just go along for the ride, because you're not computing the entanglement entropy of B, you're computing the entanglement entropy of A, and you've traced out B. Effectively, the new proposals say that following ideas that people have been talking about in quantum gravity for now decades, that since B is gravitating, you must include wormholes between the gravitational replicas. That's the new prescription. So there are these kinds of saddle points, and there are these kinds of saddle points. So then you fix their topology and the geometry, the replica geometry. You compute the CFT correlators, and then in B, because there's there's classical gravity, semiclassical gravity, you must compute the CFT stress tensor in B after tracing over A. You find the back reacted geometry. You got to deal with the gravity, and then at the end of the day, you should just find out which of these saddle points dominates. Here you have the back reacted gravity geometry in the usual sense of effective field theory coupled to a background semiclassical gravity. So the outcome from this analysis is that the fully disconnected, namely the zero wormhole, and fully connected saddles, that's this one, exchange dominance at low and high entanglement temperatures. But entanglement temperature, I mean, notice I sort of set the entanglement up with an e to the minus beta EI. So the beta controls entanglement temperature, the amount of entanglement. So, here's an example using a replica geometry with wormholes connecting all of these things. And at the end of the day, if you work this out explicitly, you will find an island-like formula for these kinds of disjoint universes. And you can use this to study entanglement between de Sitter universes containing black holes and the unitarity of gravity in a cosmological setting, as we do in these examples. I like this setup very much because it is extremely clean. There's none of this gluing, this, that, or the other, and makes it very clear that it's these wormholes running between the Renyi, between the gravitating Renyi replicates that's producing this effect of this island formula. So the wormholes somehow know about the underlying space of states. Okay, so I have is it 5 minutes right now or 10 minutes?
You can go for 10 minutes.
Okay, so if I have 10 minutes to speak, then I am actually going to sort of wrap this talk up by saying one more thing, coming from a paper with Arjun and Simon and Tomano. So, so far, the entire thrust of the talk has been, well, we would love to know how quantum gravity is unitary, and by including these Euclidean wormholes between the gravitating replicas and in these kinds of settings, we're able to recover, quote, a unitary page curve, namely a page curve that either flattens off or goes down. In any case, a situation where the entanglement entropy of the radiation degrees of freedom doesn't increase without bound, which would violate unitarity. So you can escape the violation of unitarity, if you like. Let me put it like that. But we also have many examples, well, many examples. We also have a couple of examples now where the same wormholes seem to also suggest that quantum gravity should be described by statistical ensemble. So let me say a word about that. So maybe the simplest, and that's in tension with what I said first. So how does this arise? So remember the island formula, as we described a moment ago, arose from including space-time wormholes in the gravitating path integral. So if you do a Euclidean path integral, a sum on space-time wormholes of this kind, right? I'm not doing the replica trick now, I'm just doing the Euclidean path integral for gravity. A sum on space-time wormholes is actually equivalent to a sum on baby universes. Why is that? Well, suppose I have this universe that's propagating up in time, and I have this Euclidean wormhole, the space-time wormhole. If I put it there and I slice here, now I have two circles. At that point, there's a baby universe there. So Marolf and Maxfield, Saad, Schenker, and Stanford, and others have tried to argue that this implies that you should describe this quantum gravity using an ensemble of theories. So I'm going to test a little bit how this works to try to clarify by generalizing the topological model of Marolf-Maxfield to include spin structure. So this is going to go a little bit fast, but feel free to ask me questions afterwards. I'm just going to try to give you the overall outline of what happens. So in these toy models, it's even more simple than the things that we've been talking about so far. So it's a 2D topological gravity, and we're going to consider a case with spin structure. So we're going to suppose that suppose you want to do the path integral with the boundary condition that you've got three boundaries like that. This is that two-dimensional topological gravity. That the path integral we want to study is a sum over all two-dimensional orientable manifolds, let's say with n boundaries. And I'm going to further imagine that there are periodic or anti-periodic Neveu-Schwarz-Ramond boundary conditions for fermions on various of these boundaries. Okay, so I'm going to sum over geometries that have spin structures like this. And then we're going to weight the path integral following Marolf and Maxfield by the Euler character of this topology. And then furthermore, we're going to weight it because we're taking a sum over all possibilities consistent with the boundary conditions. We need to weight it by the number of spin structures that are consistent with the boundary conditions. Okay, so that's the setting. Sum over all topologies and an element of topology spin structure. So sum over all spin structures, and we specify as boundary conditions how many boundaries and which ones have odd and even boundary conditions. Great. So you can interpret this if you like as in terms of baby universes. So if you slice open the path integral with m boundaries with a certain number of boundaries, m ns and m tilde r boundaries on one side, then the path integral on one side of that slice defines a state, if you like, with a which we'll call zm z tilde m, which tells you how many ns and Ramond boundaries you have. And then of course the path integral on the other side defines the conjugate state. And so the full path integral you can understand as creating the path, the inner product between certain number of boundaries of certain kinds and certain other numbers of boundaries of certain other kinds, and the path integral tells you the inner product, right, according to the usual definition. And if you like, you can think about this by saying that I'm going to define the Hartle-Hawking vacuum, so that's a no boundary vacuum, and then I imagine operators that create boundaries on that vacuum. So those are these z hats. So then really what the path integral is supposed to calculate is I have the Hartle-Hawking vacuum and I compute the expectation value of boundary creation operators in the no boundary vacuum. So that's the setup of this kind of topological gravity that was discussed in Marolf and Maxfield. So in our case, this is extended a little bit to include spin structure. So if you do this calculation, you have to do a whole bunch of combinatorial sums, you do that kind of thing, and use various people's results. You find the answer that the correlation function we just talked about of in the Hartle-Hawking vacuum of operators that create ns ns boundaries and nr Ramond boundaries takes the following form. Okay, this is a bit complicated, but I want to, and that's the answer for the bulk gravitational path integral. Now, if this answer for the bulk gravitational path integral had an interpretation, a standard interpretation in terms of holography, it would be interpreted as a boundary in the boundary theory as a product of partition sums where you have trace of one on the NS boundaries, and you have trace of -1 to the F, Witten indices on the Ramon boundaries, and you sort of multiply up the partition sums and Witten indices on the NS and Ramon boundaries. That would be the standard interpretation of this path integral, were you to follow your nose in the usual way to get a dual interpretation of this bulk gravity path integral. Okay, but actually, if this is the bulk answer, you cannot write down an interpretation like that. Here's why. So look at this expression, right? If you look at this expression for the bulk path integral, it vanishes anytime NR, the number of Ramon boundaries, is odd. So if it were the case that this thing had an interpretation as a product, just, you know, every time you add a Ramon boundary, you add another factor of the Witten index, then that couldn't be the case. It can't vanish if the number of Ramon boundaries is odd. So the fact that this vanishes for any odd number of Ramon boundaries tells you that it can't possibly have a standard interpretation. Standard-like interpretation in terms of product of partition sums on the independent boundaries of the system. So this is a kind of distilled version or a simple version of the argument that gets made by Marolf-Maxfield, as well as Saad, Schenker, and Stanford, that these kinds of space-time wormholes necessitate an interpretation that isn't just in a standard interpretation, a product of unitary theories in the different boundaries. In this case, we're illustrating that by using the spin structure. So, so what do we make of this? So, in fact, the same partition sum for the bulk topological gravity does have an interpretation ensemble. So what you can do is you can take the same expression and imagine in your head that you're considering n copies of theories with d-dimensional Hilbert spaces, n for the n boundaries, each of them with vanishing Hamiltonian. You imagine NS boundary conditions on the NS boundaries and NR boundary conditions on the Ramon boundaries. That's all kind of standard, as it would be in ADS-CFT. The standard path integral in these circles computes the product of partition sums and Witten indices. And then you interpret this first sum in the bulk gravitational path integral as an ensemble average with Poisson weights over the dimension of the boundary Hilbert space. That's like what happens in Saad, Schenker, Stanford, etc. Then the second sum you understand, you interpret as a ensemble average again over a set of theories which you sample with binomial probabilities, and then you get to have each of these theories at n fermionic and d minus n bosonic states, and so and as you titrate these, you get these different pieces in the sum. Okay, so you could give this an ensemble interpretation. While that might seem contrived, that's exactly the kind of thing that's been going on with Marolf-Maxfield, Saad, Schenker, Stanford, etc. You do a bulk path integral, and then you say, well, if I squint at this, I can interpret this as an ensemble sum. So thus, this topological model of gravity has an interpretation in an ensemble of field theories. Okay, so what do we make of that? So this is my, so I'm going to end here, basically. So to me, this means that there is some sort of basic tension that I think we still as a community are trying to sort out. So on the one hand, the page curve for the entanglement of Hawking radiation is reproduced in semiclassical gravity by an extension of the Bekenstein-Hawking formula that includes these islands. We're able to justify these. That seems nice. We're able to justify this by using Euclidean wormholes and so on. And you can plausibly derive it using holography and so on. So then that raises a question. How does the Euclidean path integral know about the microstates in order to be able to recover the unitarity of the page curve? How does the Euclidean path integral know about the finite dimension of the Hilbert space, if nothing else, sufficiently well in order to be able to recover the page curve? But then at the same time, as we just said, in some circumstances, the space-time wormholes seem to force an interpretation of dual ensemble, and that's definitely in tension with saying that there's a unitary description of the system. So, in some sense, actually, having though it has to be said that if you have an ensemble interpretation of the system, that doesn't preclude a declining page curve. The fact that the page curve increases and decreases, or increases and stabilizes and doesn't increase forever, is basically a reflection of a Hilbert space that's finite dimensional. It's not really, in some sense, a reflection of unitarity in the sense of being able to recover the original state through which has evolved unitarily. So, well, but this needs to be sorted out. So that's something the community is thinking about. I have one more slide, which is just a speculation for something I've been thinking about. So, I've been thinking about this sort of ensemble of theories that comes out in the picture we just talked about. And all of these settings are a little bit Baroque and in some ways artificial. There's a topological gravity, or there's, JT gravity, etc. I've been wondering if there's any other setting in more conventional string theory where I remember or I can recognize an ensemble of theories popping up. And there is one, and I'd like to take one slide's worth of time to tell you about it. So consider a universe that starts off at t equals 0 with a beginning of the world brane. So this can be a decaying D brane. So really, I'm explicitly thinking here of Sen's constructions of decaying branes, Ashok Sen's constructions of decaying D branes, almost 20 years ago now. Okay. So in these settings, you can imagine an S brane, as it's called, at the beginning of time, and the S brane decays away and eventually produces some closed string space-time. And you can show very, very explicitly that if you add fluctuations to this initial brane by putting operators on it, that leads to perturbed excitations in the bulk, and you can compute emission rates and everything else. So there's an explicit computation, for example, in this paper with Nico Jokela, Keskivakuri, and Majumdar, that shows that the theory of the emissions from this beginning of the world brane can be computed explicitly. I mean, it's a detailed and explicit calculation in an ensemble of SUN matrix models. So that's an ensemble of theories. And in that construction, later times are associated very loosely to larger n. And very loosely, time in the bulk is associated to the chemical potential of the SUN ensemble. So as you titrate the chemical potential, you're calculating quantities associated to later and later times in this bulk space-time. So that's the one previous time that I've actually seen an ensemble of theories appear. And I wonder if there's some connection, or some connection could be made, or what's going on is that somehow inherently in these recent constructions, we're talking about things that begin and end in time. And if you talk about beginning and ending in time, that's very confusing. How do you write down a dual for a theory with a beginning in time is an open question that we haven't fully understood. And I wonder if that's where the ensemble nature of these theories is coming up. So I'll leave you with a thought. It's just a speculation, but I thought it was interesting. Thanks.
Okay, thank you very much. So it was a fantastic talk. So maybe we can unmute your microphone and clap up. Yeah, so this is the time for questions. So I think I will give the microphone to Loga because he had some questions. So Loga, over to you.
Hello.
Hello.
So hi Vijay. So I had like one question regarding the first part of the talk and the other one regarding the second part. But maybe I will ask the second part first because you you have already the slides up. So when you're doing this sum over geometries and you're arguing that the sum over spin structure doesn't quite factorize and so on.
Yeah. I
was wondering whether you can restore factorization in some simple way. Maybe you can, is there some way you can see where maybe, you can put some kind of a Wilson line or something. You don't take the geometries to be completely smooth, but you somehow change the summing prescription. This is somewhat of a big question, but since the sum itself is simple, is there something that you can simply add and make it factorized?
I mean, so one kind of thing, so the detailed answer to that, I think, is not known in general, or how you're supposed to do that in general. So one way of trying to get things to factorize is to insert, appropriate projectors here that somehow are talking about, suitable superpositions of these things with different boundaries, and that can help things to factorize. But I think the detailed answer to your question is that it's not completely clear what to do to get a factorizing path integral in general. I actually see that Simon Ross is on the audience. So Simon, do you want to say something? Maybe not.
Yeah. Okay. I mean, I was just thinking that maybe you can add some more holes. Maybe you allow yourself to add interior holes or something. I don't know.
Yeah, no,
But okay.
some ways of trying to do that involve you add an additional auxiliary boundary and use the additional auxiliary boundary to soak up, some of the some of the path integral, and you can try to get the thing to factorize that way. So there's various kinds of tactics like that have been tried. If you look at the paper by Ralph Maxwell, also if you look at our paper, we discuss various approaches to trying to make the thing factorize.
But there's no simple thing that is known.
I'm not sure what those things mean is the thing. So, I mean, they're all good to try, and we have to understand that. But, basic definition of the path integral is this.
Yes, I agree.
There's a boundary condition, and I'm supposed to do the sum. And if I'm introducing additional elements to make the thing factorize, then the question is, well, it's good to know that you can, but why should I? And so there's something up in the air there that I don't fully understand.
Okay, so let me just shift and about this first part of the talk. So where you had these R1 and R2, if you could.
I'll go back there.
Yeah, where you had. So I should say that I was a bit confused on what the general prescription is. Like, should we sum over all the geometries of all the gray geometries, or should we not? Because on one way, we might want to sum over all the end of the world states. So that sounds like I have to sum over these gray geometries. But yeah, but it also has a boundary, seems to be. So yeah, how should I?
So your question is also related to some of the questions I think Emil was asking some time ago. And, so first of all, there are clearly some aspects of this sort of gray geometry, inception geometry, that are related to the states and possible states on this end of the world brain. But the asymptotic structure is not supposed to, right? This is supposed to be a commitment to what you think the Hilbert space of the radiation should look like, whether you split it or not. It's a good question as to what the rules are. Should we be summing over these things? Should we cut these things off and sum over them? Should we keep one fixed geometry? Emil was basically asking, why did you pick this one? Why not pick some other one, right? And things like that. That's all very reasonable. And I don't think the answer to that, I don't think as a community we come to a decision on what to do. I'll tell you how I think about it. So I think about any given choice of asymptotic boundary here as a particular representation of the purifier of the end of the world brain, or the Hawking radiation. So I imagine, for example, that I've done something in this case, I've got R1 and R2. I imagine it's like I've taken the Hawking radiation, taken the early stuff and the late stuff, and the early stuff and the late stuff somehow sit very far apart on a Cauchy surface, right? Because some of it came out here, some of it came out here, and I've got them well and separate. So they don't really interact. So I've separated them, and then I do some further, unitary transformation to get two disjoint pieces of that Hilbert space, so they don't interact much. And then this is supposed to be a picture putting them apart. So if it's split into three parts, it would be like separating it into three parts. It's like turning the Hilbert space into sort of factorized pieces, if they were, or finding a basis where they're pretty factorized. So that's what this is supposed to be, at least that's the way we think about it, right? So, but I think overall, in the end, this is some, what's being described here is a toy model, right? I mean, I do think that if you want to describe the Hawking radiation in the basis that we get the Hawking radiation, which is the normal particles that comes out, it's probably not this basis, right? This is some unitary transformation of that basis. And I do not, and that's, as such, it will be some kind of superposition of these things or something like that. And how we're supposed to think about that is not so clear, right? So that's like asking ADS-CFT, if I have a superposition of different boundaries, right? Is there a meaningful sense in which I can talk about this kind of duality? And I don't think I know the answer to that. But these are good questions to ask, and I think these are all fun things to try to sort out. Certainly, we're thinking about some of them. Yeah.
So just one more follow-up question, and then I'll just end. So if you connect A to some interval or something, some region, okay, I can identify some local subregion there.
Sorry, I'm trying to recover the page. Okay, please go ahead.
Yeah, and I was kind of trying to see can you actually explicitly say which operators in this external system that I'm connecting correspond to R1 and which one correspond to R2? Like if I insert an operator in this external thing, can I actually work out what I should do on the R1, R2, or like how explicit is this construction? Would it allow me to answer these questions? Yeah.
Right. That is a very good question. And the answer, zeroth order, is that at the moment the construction is not explicit. We simply declare that we split it into regions R1 and R2. And explicit construction would involve an ability to say, I have the original boundary A, I have the degrees of freedom there. Here's a transformation, some basis change, if you like, of A, and then I identify for you within that basis change what sits in R1, what sits in R2. So we haven't done that. And it would be nice to do that, to be able to identify, useful separations of the Hawking radiation into two pieces. Now, I personally think that a natural separation is the early and late time radiation. So I personally think it's at my head that R1 is like, let's say, early time and R2 is like late time, and that maybe what I can do is, because these things don't interact much, and that maybe whatever basis change is necessary to produce the operators that are well separated into R1, R2 will have the character that they're kind of local on a Cauchy slice, far away on one side versus far away on the other side, reflecting where the radiation has got to after a certain period of time. That's not constructive. That's, I'm stating some kind of intuition for what should happen, and that remains to be done.
Thanks.
So there is a raised hand by Bharat Kumar. So Bharat Kumar, you can unmute your microphone and ask your question.
Yeah, hi. I had a very basic question about the CFT that you're inserting at the inception disk, if I got it correctly. So the first one was that, are there any restrictions on the central charge, in the sense that do you still expect this to be some kind of a semiclassical CFT, and whether there's also a restriction on the operator spectrum?
So two things. So in order to do this sort of inception construction, you do need the thing to be semiclassical, as in C should be large. So there's some analysis which I can't reproduce directly at the top of my head of regimes of parameters in which C as identified for that end of the world brane will be large. So you do need that to be large. So in some sense, if you have if you have a holographic dual, as we know that there are restrictions to the operator spectrum in typical holographic theories, there's some character to the thing, it has to be semi-classical and so on. So the gaps have to have a certain structure and so on. So have we checked that? No, we haven't. We've assumed that the end of the world brane has that characteristic. Again, it would be better for any of these end of the world brane constructions to have a explicit construction from string theory, where you have some actual brain system sitting behind the horizon, blah 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 blah. You fiddle the parameters, you can analyze what C is, the thing is semi-classical, what the operator spectrum. That's what we would really like, fully microscopic understanding of these things, and then we would feel fully satisfied. So all of these end of the world brane constructions, including ours, have to be understood a little bit in the toy model sense. But in order to be self-consistent, they have to satisfy the restrictions that you're mentioning. And you can check whether it's self-consistent to impose those restrictions. And we did.
Okay, thanks.
Okay, some more questions from Shreyans. So Shreyans, go ahead.
Sir, I wanted to talk something about the second.
Sorry, I couldn't hear what. Could you say it again, please?
Am I audible now, sir?
Yeah, you are more audible now, but its voice is going in and out.
So you were saying something about the formation of baby universes. Meaning it's not a question. I just wanted to get some insights into how these baby universes are coming in Euclidean wormholes.
Okay, so I think this picture may help to clarify. So imagine you're talking about, a circular universe,
Yeah.
or a disk or something. So then what you do is, this is the time evolution being drawn up here. So in the absence of forget about this wormhole here. In the absence of anything, you have this disk, it's going up in time, right? There you go. And the Cauchy slices are the blue lines, and you'll get these various slices, right? There's some geometry on them maybe. Then what you do is you agree that you have space-time wormholes. Space-time wormholes are little handles that go like this. So if you have a handle that goes like this, and then you slice it at this later time, notice that you have the original kind of slice that's here, this disk, and in addition, you have a disjoint piece over there. So this disjoint piece would be referred to as the baby universe. Does that, so in this way, having the Euclidean path integral wormholes gives you baby universes. Does that
how are these handles are the replica?
So here I'm not.
These handles are the replica wormholes.
Good question. So here, we're not doing a replica calculation here. So the idea is that in the replica calculation, the statement that you should include wormholes on the Euclidean side, on the gravitational side, is simply a special case of the general statement that when you do the Euclidean gravitational path integral, you must include space-time wormholes. That is an assertion that goes back a long time, right? Decades and decades. People in gravity have been saying a long time that how do you do the path integral? You fix the boundary conditions. Here, the boundary conditions are there's a disk up here, there's a disk down here. And then you have to sum over all geometries and topologies that interpolate between these two boundaries. So that's the usual prescription for the path integral. And gravity people have been saying for some time now that you have to sum over all topologies. So actually, this is an investigation of an older idea that should be there, that you should do that sum. And in the replica setting, the novelty is to say, well, even in the replica setting, because the replica setting arises from doing a particular path integral, which involves this gravitational path integral also, even in the replica setting, you must include those gravitational wormholes. But at the same time, I think as a community, we're going back a little bit to think about the already existing problem of suppose you do the Euclidean gravitational path integral, no replica involved, just do it to compute the partition sum for gravity, then you have to include these wormholes. What are the consequences of that? So this is not a replica calculation being described here. It's a sort of broader thing, if you like. Did that answer? Yeah. Did that answer your question?
I just took some more insight into where these handles are coming from in the path.
I couldn't hear your question, actually.
Okay. So I just wanted to get some more insight as to where these handles are coming in the Euclidean path integral.
So maybe rather than saying where are the handles coming from, we should say that we are supposed to sum over all topologies that satisfy certain boundary conditions. So if those topologies include things with such handles, then you should include them. You should sum over them. There's also the question of whether or not in a sector that has such a, a more complicated topology like this, whether there's a saddle point geometry, right? So you have to sum over topologies, and in each topology, you need to see if there is an actual saddle point. So in some cases, you can try to cook up a topology with funny handles and things and everywhere, and you may find that there is no actual saddle point to the metric. There's no solution to the equation of the motion with that topology and these boundary conditions. And if that's the case, that topology will not contribute because, or will not contribute much. It'll, you can still sum over it, but there's no saddle point, so it won't give a big contribution to the path integral. So really, at the end of the day, you imagine you study all possible topologies, satisfying the boundary conditions. You sum over, in each topology, you have to sum over all metrics, and then those topologies that support saddle points of the gravitational equation of the motion will give a large contribution to the path integral. Does that answer your question?
Yeah, am I taking too much time for other audience? If not, I just had a last question.
It's up to the organizer.
Yeah, go ahead.
Can I ask? Okay, thank you. So do we find wormholes in CFT path? Why is it that it's only in the gravity path integral where we move over all topologies? It could be possible that in the CFT itself, if we sum over, is it because topologies are.
So your voice was cutting in and out a bit. I think your connection isn't great, but I think I heard part of the question, so let me repeat it back. And if it isn't, put in the chat box that this isn't the question you were asking. I think the question you asked was to say, well, why should you sum over topologies in the gravity path integral, but not in a regular CFT path integral or a field theory path integral? I think that was the question you asked. Well, so the usual way in which we define a quantum field theory is there's a fixed background. You don't even sum over metrics, by the way. You fix the background metric. And then on that background metric, you define some action for a quantum field theory. It could be a conformal field theory, but any field theory. And then what you do is you sum over all the quantum fields on that fixed background. That's the definition of quantum field theory. But if you sum over metrics, then you're starting to do gravity also, because gravity is sum over metrics with some action. So now you could ask the question, when you do the sum over metrics, because it's gravity, right, somehow having to do with the structure of space, am I now supposed to start summing over topologies too? And you could debate that, whether you should or shouldn't. And the feeling, at least amongst people who do Euclidean gravity, Euclidean quantum gravity, has been for a long time that a consistent definition requires you to actually sum over topologies also for gravity, but not necessarily field theory, because the idea is the path integral is really summing over all ways of going from, let's say, some initial configuration to some final configuration. So you just need to get from one configuration to another configuration, and any way of getting in the space of configurations from the first one to the final one is fine. So in field theory, that is, you fix the background, you sum over all possible configurations of fields, right? All configurations of fields. And in gravity, you also sum over all configurations of the background. And the background here can involve geometry and topology. So I hope that answered the question, if I understood the question correctly.
Yeah.
Sorry, Shreyans, you are not audible. So if you have any more questions, you can write in the chat box.
Yeah, I'm fine. Thanks a lot, sir.
Okay. Okay, so any other questions?
Can I ask another one if there is no one?
Hi, I have. Okay.
Sorry, Shreyans, Akhil is in the queue. So maybe Akhil, you can go ahead.
Yeah. So there's a step in which you showed that the islands naturally arise when you purify with the theory with gravity turned on, right?
Yeah.
So I didn't understand, why did we want to purify with the theory with gravity turned on again?
That's well, we did is perhaps the answer. So how to put this? So suppose B didn't have gravity, you wouldn't get these islands. And if B does have gravity, you will. So that's a statement that's interesting to understand.
No, I understand it's in parallel with like having holographic duals to the deep end of the very deep brains and so on. That's where B has a gravity.
There's no holographic dual in B. So B is just a theory that contains gravity and a field theory, and A is a universe that contains just a field theory. This is investigating the question of, I have one thing that contains gravity, and I have another thing that doesn't contain gravity. The oddball thing that seems to happen here is that, and remember, the gravity here is semi-classical even. The gravity isn't the full quantum gravity. In the end of the day, like in all of these calculations, we simply put the gravity thing on its saddle point. We do some back reaction and we complete the action. There's not a real sum over metrics and things being done here, other than agreeing that you're allowed to use different topologies and complete the saddle point. So semi-classical gravity. The statement that's unusual is that normally, so the statement that's unusual is that suppose you now trace out, right, B completely, forget about B, and write down the density matrix on A, and you compute the entanglement entropy of a density matrix on A. The sort of strange thing is that in the semiclassical description of the system, you will find a formula that involves the surface area of an island in B. So the number you get by computing the entanglement entropy in A equals something that includes the surface area of an object in B. So that's a surprise. And part of the reason that's interesting is, of course, you know, the surface area over 4G Newton is the same thing that appears in the entropy of black holes in our universe. And, you know, there is gravity in our universe. So you could, so one wonders exactly what the connection between these things is. But this is a very, would you have expected that to be a statement? I wouldn't have expected that to be a statement, right? You give me A entangled with B, B happens to be gravitating. I happen to go off and compute the entanglement entropy of A. The number I get involves the surface area of a little piece of B. That's a very unusual thing to happen. But it does if you use this prescription.
So just to clarify, so if you also had gravity in A and you were to do this calculation again, would you consider like replicas where A and B are also connected and so on?
I think you should. No one's done that. It'd be interesting to do.
And just another point, like as in like so you started with the theory in just A without gravity, and you want to calculate the entropy, and when you turn to have when you decide to have gravity in B, like what decided what choice of gravity I should have in B, or does it not matter?
The choice of gravity was dictated entirely by I can calculate. So the gravity in question being used here is the JT gravity. So let's take the substantive part of your question, which is that if I had chosen a different kind of gravity here, would I have got a different result, right? So this isn't, or is it somehow something very special to JT gravity? We certainly don't expect that it's special just to JT gravity. That's why I did that three-dimensional example to start with. That's not JT gravity that we're talking about when we're talking about the 3D BTZ black hole and things like that. That was tried to see if we could extend beyond. But here we're using JT gravity for a number of reasons. There are many technical simplifications in JT gravity. So for example, when you compute the back reaction of the matter fields, it leaves the metric alone and sort of back reacts in the dilaton. Yeah. And so that makes things much simpler. So this is a very simple theory of gravity, so you can calculate. So always, you know, the trick or difficulty with working with theories of gravity is actually getting an answer, right? Calculating something. Here you can calculate. That's the reason we choose this.
Any more question?
Am I audible, sir?
You should type it in.
Am I audible, sir?
No, I can't hear you. So you should put it in.
Okay, sir.
Yeah.
Chat box. What does it mean that we're considering? I guess this is the question. Is that the question?
What is breaking? Maybe you can write it in the chat box.
No, I'm writing it in the chat box now, sir. So, by the way, am I audible?
Now you are.
Okay, thank you, sir. You also told us something about the mechanism of the formation of the islands, maybe in some part of your talk. Secret sharing, quantum, I don't exactly remember. There were, how should I say? So can you, if it's not taking your time, can you re-explain how you, what you suggested was the mechanism for the formation of islands in, what was the mechanism for the formation of islands at late times?
So I'm not sure at what level you mean the mechanism for the formation of the islands. So at some technical level, the
there was some slide which I wanted to move to, sir.
one of these,
Not this one, sir.
this one,
No, sir.
this
Yeah,
one,
secret sharing in Hawking. Yeah, secret sharing in Hawking radiation, sir.
this one,
Secret, sir. Secret sharing in Hawking radiation.
this one.
Sir, secret sharing, yeah, secret sharing in Hawking radiation.
Yeah.
Yeah. Sir, I just wanted to get some comments as to how the information about the Inception region is getting encoded in the in some sub region of A. You made some comments about it, but it really went too fast for me. Yeah, this points to quantum secret sharing in the radiation. The third point which you have.
Here that I'm trying to make is that if you look at the heights, if you look at the entanglement wedge of R1, it contains this region behind this dark purple line. The entanglement wedge of R2 contains this region behind this purple line. So it's if I look from the right side of this picture, it involves the outside region here that is not colored. But the inside region is not contained in the entanglement wedge of either R1 or R2. So that means that this inside region cannot be recovered by entanglement wedge reconstruction separately from R1 and R2. So, however, if I take the union of R1 and R2, the union of these two things, then the original black hole horizon is homologous to the union of R1 and R2. So because it is homologous to the union of R1 and R2, the entanglement wedge of the union of R1 and R2 includes the entire black hole interior. It's everything outside and the interior. So that includes this purple region. So this points to, quote, quantum secret sharing, because the union of the information you can get by taking, a partition of these degrees of freedom is not equal to the information that you can get by taking the union of those regions first. Well, the reconstruction with the union of the degrees of freedom is not the same thing as the union of the reconstructions of the from the subsets. So that's basically points to quantum secret sharing.
Thanks a lot, sir. I am very sorry for the trouble, sir.
Yeah, I think we should wrap it up. So Vijay, thank you very much. So it was another wonderful talk. I listened from you.
Thanks so much for inviting me, and this was a lot of fun. And thanks to everybody for all the questions. That was great.
Yeah, great. So have a nice time. Bye-bye.
Bye.